All right, gang, on we go in our study of complex analysis. So this is the second lecture after we separated to remote learning. So the goal in this first part of lecture 2 is to understand a theorem that in the last lecture I said we weren't going to look at, but as I thought about it and ran some examples, I just realized that we should see it. So I want to state for you the Cauchy-Integral theorem for multiply connected domains. And I thought I would start out with a picture and actually write down the statement of the theorem based on the picture because it really will help the other statement that's a little bit technical make a lot of sense. Hopefully, that's the goal. So here's the idea. You've got this larger contour C, I'm going to assume positively oriented. And then inside C, you've got a finite collection of other contours. These are all simple closed contours. And the way that I'm going to state the theorem, the little ones inside and the big one that's enclosing them all have the same orientation. I'm assuming positively oriented. Actually, you can just say they're the same. There's a way you can state this theorem when they're opposite. So when the big one goes one way and all the little ones go the other way, but we're not going to write that version down. Your book actually does, but I think the way that I'm going to say it is much easier in practice. Okay, so what is this theorem saying? Well, if you think back to the corollary that I ended with last time, you might pause the video and go look at that real quick. If you look back on that corollary, what you might expect is that the integral over C of f of z dz, we'll talk about the conditions on f in a minute. This integral, you might expect this to be the integral over C1 of f of z dz plus the integral over C2 of f of z dz plus the integral over C3 of f of z dz. And you'd be right. That's what this theorem says. The condition on f is that f needs to be analytic on all of the actual curves. So it's got to be analytic on all of the c's, and it actually needs to be analytic inside the blue region. So what I'm saying is it needs to be analytic inside the big curve, but outside the little curves. Okay, so f is analytic on the blue region. And then I don't care what happens inside the little ones. So it can be very bad there. It can have bad points there and misbehave. That's fine as long as we can enclose those points in a closed curve. We're good. And so that actually is a particular example of the Cauchy-Integral theorem for multiply connected domains. Let's look at the full statement of it. So here it is. I didn't want to write it out on the screen because it would take so long. I guess it's kind of boring to read it, but that's okay. So C is positively oriented simple closed contour. That's our large C, our big C, the C1 through Cn. These are our little c's inside. I'm going to say they're positively oriented, simple, closed. They lie inside C. And then here is one technical condition that's important. I want none of the interiors of the C's to overlap. It's okay if the curves bump each other and share a point, but their interiors can't overlap. Does that make sense? So then here's the statement that we just said. F is analytic on the curves, and then it's on the region inside of C and outside of each of the CK. It's just the blue region in the picture. Then the integral over the big contour C is equal to the sum of the integrals of F over the smaller contours C. And like I said, there's another way to write this. Actually, let's talk about it together. So what happens if we state this the way your book does and we reverse the orientations of the C? So now they're opposite. Well, if you think about it, then all that I've really done by changing the sign is now these integrals are all negative. Just slap a negative out front and move this across. And so your book says this guy plus these equals 0. Because they orient the little c's in the opposite direction of the big C. I like to orient them all the same. I like the idea of collapsing. The way that we've said it is you can collapse the large curve down to these smaller curves, and that I think is the best way to think about it, and you can see it in the picture. All right, so that's a theorem. I'm going to use it in an example down the road, but I want to do another theorem with you first, and that is going to be called the Cauchy Integral Formula, actually. And so let's pause. We'll stop this video, and then we'll pick the next one up with